These are the frequently asked question videos for Algebra 2 for section 6.2, day 2. I'm going to start here with number 41. And what I noticed right away is that there's some division here that can take place that they didn't really want me to see. Otherwise they would have put that together. So what I'm going to do is go ahead and do the division under one cube root symbol and see what I have, because I can, like I said, obviously see that 48 divided by 6 is going to give me 8. And that takes something out of the denominator, which is going to be really helpful. So 48 divided by 6 gives me the 8. And then I have my x's, which if you're going to divide similar bases, you subtract the exponents. So that would be 3 minus 4, which would be the -1 power. I'm just going to go ahead and move that down right away as a reciprocal. Move it down into the denominator to get rid of the negative. And then y squared and y, again that's division of similar bases, so you subtract the exponents, but 2 minus 1 will give me a positive 1. Now that's a lot easier to work with. So really what I have is the cubed root of 8, and then I have the cubed root of y, and then on the bottom I have the cubed root of x. And we know, of course, we can't leave that cubed root of x down there. So this is a power of 1. In order to get rid of it, I'm going to need to have at least an x to the third. So I'm going to multiply my denominator by the cubed root of x squared. Because remember, when you multiply similar bases, you add the exponents. And 1 plus 2 will give me that 3 that I need. But whatever we do to the bottom of the fraction, in order to keep it equivalent, we also have to do to the top. So now I want to simplify as I go, but I really want to focus on that denominator and make sure that everything is going to come out like I want it to. So x to the first times x squared is x to the third, and the cubed root of x to the third is x. So that's going to work out great. And now I can simplify in my numerator, and I have the cubed root of 8, which is 2. Cubed root of y, nothing I can do there. Cubed root of x squared, nothing I can do there. So cubed root of, that will be x squared y. And I will just simply keep moving that over. So I have 2 cubed roots of x squared y over x. Then I go back to the original to see whether or not I should worry about absolute value bars. And this was cubed root. So cubed root does not require any absolute value bars. So this is my answer right here. 2 cubed roots of x squared y all over x. Number 42. Kind of similar. You know, you look at this and you see right away there are things that could be reduced here, and that might make the problem a lot easier. So I'm going to go ahead and put that under one square root symbol and do some reducing and division and see if that helps out. So 20 and 45, pretty obviously 5 will go into both of those. So we will have a 4 and a 9. And then with the a's, again, to divide similar bases, you subtract. 1 minus 2 would be -1, but I'm going to go ahead and move that down into the denominator right away to eliminate negative exponents. And then b to the first, again, we're dividing, so 1 minus 3 is -2. I'm going to go ahead and put that b squared down in my denominator. Now, let's see if I can get this to move up a little bit. There we go. Some good things have happened here. I mean, we now have perfect squares that we can see here. So I'm going to go ahead and separate things and see if there's any problem in the denominator. So the square root of 4 is 2. That's good news. Square root of 9 down there would be 3. Square root of a, nothing I can do about that just now. And then the square root of b squared is a nice b. So things are looking much better than they did at the beginning. But I still have that square root of a in the denominator. So what I have to do is multiply my numerator and my denominator by the square root of a. So my numerator will be 2 square roots of a. And on the bottom I will have a nice little 3b. And then it'll be the square root of a squared. And of course the whole reason we did that was because the square root of a squared is a. So that will be 3ab down there in my denominator. And then 42, this one was square roots, so I want to go through and check and see whether or not I should be worrying about having any absolute value bars. And I notice up in the original, whoever wrote this problem did not care whether or not A's and B's were negative and that people would have to write no real solution. I see that because there are odd powers of them up there. And so that means I don't have to fuss with the absolute value bars at this point. That this will be my answer. If they had cared, they would have made sure that their formula was restricted only to positive values as they went through that. All right, then, those were some good problems there. Number 45. I don't know that this one will give you a lot of trouble, but I thought I'd just go through this. We've got cubed root of x, cubed root of 2. The reason I'm doing this one and not 43 and 44 is because this is cubed root. So, you know, a little more than we're used to. We've done square root a lot in exponential algebra. So I have a 2 down here in the bottom, and if you make a factor tree for 2, that's it. It's 2. It's 2 to the first. That's your prime factorization of 2. So what I have to do is get this 2 to the first to be 2 to the third, so that will cancel out. So what I'm going to have to do is multiply by the cubed root of 2 squared, which is, of course, the cubed root of 4. Note that those are the exact same thing, that I've just written it differently. And the reason that I did that is so that you can see how this denominator is going to work out very nicely. If I have the cubed root of 2 to the first and the cubed root of 2 squared, and I look at that 2 as a base, that means I'm adding those exponents. And of course, the cubed root of 2 to the third is just going to be 2, which is beautiful. We do not want to have that radical in the denominator, so we have rationalized the denominator. My numerator, I'm just going to have the cubed root of 4x. And then, of course, we take a second to see whether or not we should have any kind of absolute value bars on this one, and the answer is no. This was cubed root as we go through it. So this was all about rationalizing that denominator. We scoot this up just a titch here and go after number 56. Oh, I'm sorry, 46. So 46 has the cubed root of 5 over 3x. And we take a look at that and we see there isn't any simplifying we can do. So we're going to go ahead and separate that. And notice I've got a couple of problem areas down there in my denominator this time. I have a 3, which again you make a factor tree for 3, and that's it. It's 3 to the first. That's your prime factorization. So what we have to do is we're going to have to multiply by the cubed root of 3 squared, which is the cubed root of 9. Notice that what's in the red there is really 1. We're doing the cubed root of 9 over the cubed root of 9, just written in different forms. And that is that's what we do in algebra. We're manipulating. Then I also notice down there in the denominator I have this nasty little cubed root of x. I'm going to need that to be a power of 3, so that'll cancel out. So I need an x squared on the top and the bottom. Again, as you look at what's in the red, that is 1. That is all that is. So we're making an equivalent expression out of this. On the top, I do my multiplication, and I have 5 times 9 is 45, cubed root of 45x squared. And then on the bottom, I will now have the cubed root of, if we use 3 as a base, it will be 3 to the third, x to the third, which is great news, because that's going to be 3x. And I take one last look at my numerator because I'm checking out that 45 and I'm trying to see, are there any perfect cubes that will divide nicely into 45? There are not. That's done. And because it's a cubed root, I do not have any worries about absolute value bars. Now, I think I'm going to erase. I'm going to try to scroll everything up here and go after number 48. As I look at number 48, I see there's a lot that I could do with this to get it started. First of all, 15 divided by 3 is 5, so I'm going to write that down right away. And then I notice, hey, 60 divided by 12, that's going to give me something that I can reduce there. So I'm going to go ahead and put the rest of this as just one big fraction and see what happens. So we have 60 divided by 12, that's 5. And then we have x to the 5th being divided by x to the 1st, that's going to be x to the 4th. So my what was 15 thirds becomes 5 over 1, and then I have the square root of 5x to the fourth. So I have my 5, square root of 5, nothing I can do with that, but the square root of x to the fourth is x squared. So this will be a 5, square root of 5, x squared, which will be 5x squared square roots of 5, putting the radical in the back on that one. And then for 48, we'd want to talk about whether or not we need absolute value bars here. And the original for 48 did have x to an odd power. And that means when they wrote this problem, they said it was perfectly fine that people would get no real solution. So we don't need to bother with absolute value bars for number 48. Then, next one on the list, I thought you might be able to handle 49 pretty good on your own, so I'm going to go to 50. And 50, there is some simplifying we can do. Not everything is going to work out beautiful here, but we can certainly do some division of those variables and see what we get. The 5 halves is going to be 5 halves, it's just going to be a little obnoxious to work with. And then when we see that there's division, we subtract the exponents. So 4 minus 2 is 2, that's positive 2. That will go in my numerator. And then y to the first and y to the third, 1 minus 3 is negative 2. So I'm just going to go ahead and put that down at the bottom to eliminate needing any negative exponents there. So right now I have the square root of 5x squared over the square root of 2y squared. And I want to focus on simplifying what I can and then realizing that I'm going to have to multiply by something to rationalize the denominator. So the square root of 5, nothing I can do with that, but the square root of x squared is x. On the bottom I have the square root of 2, but the square root of y squared is y. So the issue here is the square root of 2 in the denominator, and to eliminate that, all I have to do is multiply by the square root of 2 in the numerator and the denominator. And that will give me x square roots of 10, or square root of 10x. And then on the bottom, the square root of 2 times the square root of 2 will give you 2y. Once again, we should stop and consider whether or not we need any absolute value bars. And in number 50, as you look at this, you realize the x's were always supposed to be positive because both of those were raised to an even power. That means that they always would come out positive. So no matter what, we should be able to get an x that's a positive value. Well, if somebody puts a negative into our final equation, they could have a negative for that x, so we have to eliminate that. We don't have to worry about the y's, and that's because both of those were already to an odd power. So the writer of this problem didn't care whether or not those y's came out negative and people had to write no real solution. It's all about what were they thinking when they made this formula. Then, let me see if I can fit 51 on here. Boy, does that ever look like an obnoxious problem, huh? Let's take a peek at that. So, first glance, you're seeing that 12 is definitely reducible with 10. We've got A's, B's, and C's that we can do some simplifying with. So, let's go ahead and put all of that underneath one radical symbol and do a little simplifying, hopefully, to make the problem a little easier right off the bat. All right, so let's see what we have. Well, 12 divided by 10, 2 goes into both of those, so that'll be the cubed root of, we'd have a 6 and a 5, dividing both of those values by 2. And then our A values, well, we have a 1 and a 3, and 1 minus 3 is negative 2. I'll put that in the denominator to eliminate the need for any negative exponents. For the B's, I have a 3 and a 1. 3 minus 1 is 2, so that B squared is positive. That'll go right up there in the numerator. And then my C's, C to the second, C to the first. 2 minus 1 is 1, so a nice little C up in the top. And the more that we can eliminate out of that denominator, the better. So up on the numerator now we have 6b squared c, and in my denominator I have a cubed root of 5a squared. So now starts that process of, what cube root am I going to multiply here to get rid of all the trouble that I have in my denominator? And I have a 5 down there, and if you write down 5, that is its own factor tree. It is 5 to the first, that's the prime factorization. So I'm going to have to multiply that by 5 squared so that my index and my power match, and those will drop right out. That, of course, is 25. So I'm going to go ahead and write that up in the numerator. But again, remember, what I have in the green up there so far is 1. Then I have my cubed root of a squared. Well, I'm going to need one more a in order to get that to be the cubed root of a to the third. So now I would have, up in my numerator here for number 51, the cubed root of 150. Get this out of the way so it doesn't look like a problem there. Because if you had 6 quarters, you'd have $1.50. And then we have a, b squared, c, all underneath that radical. And on the bottom, we now have the cubed root of 5 to the third, a to the third, which is good news because that will give us 5a. And then I'm just going to go ahead and think about whether or not I have any perfect cubes that would divide into 150 evenly, and there are not any perfect cubes that would take care of that for me. So finally, last thing we think about is absolute value bars, and this was cubed root, so don't need to bother with it for number 51. That's a monster right there. You know, it takes some work to think your way through all of that process. Then number 52 says we have a formula t equals the square root of 2s over a, and that shows the time t, and really this problem is about keeping track of what all the variables stand for. So the time t that any vehicle takes to travel a distance s at a constant acceleration a. So distance s, acceleration a, starting from rest, so a stopping position. What is the difference in time between a car accelerating at 16 meters per square second and one accelerating at 25 meters per square second for a distance of 200 meters? They're really asking me to calculate 2 things here and then tell them the difference between those 2. So for 52, we want the time, and the first time we want that for an acceleration of 16 meters per second, so that's going to go down on the denominator for a. And for both of these, that s, that stopping distance, is going to be 200, because they said it was a stopping distance of 200 meters. So the square root of 2 times 200 over 16. And that's going to be the square root of 400 divided by 16, which comes out to 5 seconds. Now, next time through, I'm supposed to change that a value, which was my denominator. So this is really the first time, and this is my second time here. So the square root of 2 times 200, and then we need to, whoops, make sure I have that radical looking like it's going for the whole thing. There we go. 2 times 200 divided by 25. So 400 divided by 25, and then you take the square root, comes out to a very nice 4 seconds here. And just like anything else in word problems, you always check to see did you answer what they wanted, and it says what is the difference in time between those cars, and that's going to be 5 minus 4, which is 1 second. So that's the difference there. Again, in the first one, you take 400 divided by 16, then take the square root. 400 divided by 16 is 25. You take the square root of 25 and you get 5. For the second time period, it'd be 400 divided by 25, which is 16, and the square root of 16 is 4. So keeping track of the variables is the hardest part of that problem. Then in number 53, the base of a triangle is the square root of 18, and its height is the square root of 8 centimeters, and we are supposed to find its area. Well, they said it was a triangle. Area of a triangle is 1/2 base times height. So 1/2, and our base was the square root of 18, and our height is the square root of 8. So we will have 1/2, and then we want to figure out what 18 times 8 is, and that very nicely comes out to the square root of 144. Square root of 144 is 12, and half of 12 is 6. This was area, and the units that they gave us were centimeters, so it would be 6 square centimeters. Next one on my list for you, 54, using a little physics. 54 says we have the formula F equals mv squared over r gives the centripetal force F of an object of mass m moving along a circle of radius r, where v is the tangential velocity of the object. Solve that formula for v. Wow, all of that just to say, solve this for v. Rationalize the denominator. All right, so first thing I think would be easiest to do is just go ahead and multiply both sides by r. That's a nice, easy little thing. And we usually keep those in alphabetical order. I'm going to put a semicolon here so you know this is my next step. The r's would cancel out over here, so we would get mv squared. Then we would want to go ahead and divide both sides by m. So we would get fr, put a semicolon there so things don't get all weird, fr over m equals v squared. And then finally, to get rid of squaring something, you take the square root. So it will be the square root of fr over the square root of m equals v, and we want a plus or minus there since we were doing square roots here. And then what we wanted to do, they actually reminded us, rationalize the denominator. So what I'm going to have to do is multiply my denominator and my numerator by the square root of m so that I can get rid of that square root of m in my denominator. So that means we will have the square root of frm over the square root of m squared, which is just m. Throw a little plus or minus in front of that because velocity can be positive or negative. And we should be good to go. So plus or minus frm plus or minus the square root of frm all over m equals velocity. All right, we have number 55 here. Sorry about that, drop the eraser. I'm going to go ahead and erase that piece. And wow, it disappeared. There it is. Didn't mean to erase the whole thing. There we go. So the circular velocity v in miles per hour of a satellite orbiting Earth, given by that nasty little formula there, where r is the distance in miles from the satellite to the center of the Earth. How much greater is the velocity of a satellite orbiting at an altitude of 100 miles than the velocity of a satellite orbiting at an altitude of 200 miles? And big helper here, they gave us the radius of the Earth is 3,950 miles. So again, what I have to do is do this twice, and then I have to compare the two by subtracting. So first one, square root of 1.24 times 10 to the 12th. Now the radius of the Earth is 3,950, but we would have to add the height of the altitude because we're saying it's above the Earth by that amount. So if we have 3,950 and we add 100 to that, we're going to have 4,050. And then that was my first velocity. Second velocity, square root of 1.24 times 10 to the 12th. This time the radius was 3,950, but we are supposed to check that out for an altitude of 200. Now the reason we're going to do this is I'm going to draw a little Earth here. This would be the radius, but notice if we're out here, we have an additional amount that we have to add onto that for the orbit. So in this case, this would be 4,150. And that's for that altitude of 200 miles. And then you crank this out on your calculator, and this one is 17,498. And this one comes out to 17,286. We wanted to know the difference, that means subtract. So that is 212 given in miles per hour. There it is. So difference of 212 miles per hour. All right, what did I have left for you here? Number 61. Number 61 is simplifying each expression. And hopefully you looked at this and thought, well, we just distribute. That's exactly what we would do. So you take a square root times a square root, and that's going to give you a square root. And then the square root of 2 times 7, well, you have to keep those separate. You can write them as multiplication, but remember, square roots are only multiplied times other square roots. And then this is, of course, 10. And and everything is as simplified as it's going to get for that problem. Number 62, very similar, and when you take the square root of 5 times the square root of 5, you get the square root of 25, which is of course 5. And then we would have 17, whoops, not 17, 15. I don't know where I got 17 from. 15 times 5, which is 75. And then we would go ahead and simplify that because a perfect square of 25 goes into that nicely, and the square root of 25 is 5. So 5 plus 5 square roots of 3. And there it is. Now, I think there was one more. Oh, two more. 69 says the mass M of an object is square root of 80 grams, and its volume V is the square root of 5 cubic centimeters. Use the formula D equals M over V to find the density D of the object. So, again, this is all about keeping track of what goes in for what. Mass, right there, square root of 80. Volume, V, square root of 5. You think, wait a minute, does that go into that? Oh, it sure does, and it goes into it beautifully. 80 divided by 5 is 16, and the square root of 16 is 4. So this label is going to be nasty because on the top we had grams, and on the bottom we have cubic centimeters. So that's 4 grams per cubic centimeter. Number 70, really interesting problem here. 70 is asking us if you take the square root of x to the third and figure out whether or not that equals the cubed root of x squared, which is kind of interesting when you think about it because it's saying index of 2, power of 3. Does that give you the same thing as index of 3, power of 2 for all, some, or no values of x? And explain. Well, first thing I did was I put a negative in here and thought my way through it. If you put a negative in here, you'll get a negative answer. If we put a negative in here, we're going to get a positive answer. So negatives are not going to work. And that was basically the first thing that I wanted to eliminate. Then I think about just something basic, like maybe putting a 2 in here. If you put a 2 in, 2 cubed is going to give you 8, and that'll give you the square root of 8. If we put a 2 in this, we'll get the cubed root of 4. No, those are not the same thing. You can punch them in your calculator, that's not going to work. So far, negatives aren't working, positives aren't working. Now what I need to do is I need to check the special numbers. And the special numbers generally are 0, 1, and 2. But I just checked 2 for positives and it already doesn't work. So if I check 0, yeah, 0 in both of these positions is going to give us 0. So we can put some, and 0 is one of those instances. So now I've eliminated my 2 and my 0 as special numbers. I still need to look at 1. And if I put 1 into both of these positions, then it will be equal. It'll be 1 equals 1. So sum, it's 0 and 1. That's it. Those are the numbers that are going to make that happen. We just check through the system of numbers that we have. We already know that negatives can be an issue, so that's one of the things we go after. Then we look at positives, and then we look at special numbers like 0 and 1. So that should do it for this section.